2 becomes critical. It changes everything unless you center. So it's basically recommended that whatever you have an independent variable, you center it. You either use grand mean centering or root mean centering. And you just always do that and you never worry about it. So I did that here. And that's what
using that years in school variable. So what we get to do now is fix the random effect. So I'm going to get rid of average as an outcome. Why? Can't I get this average as an outcome? I'll just choose another one. I don't have yours in school. You have it. If I did have yours in school, which I don't, and I wanted to fix my variance, I would just click on that little random effect, that little random error, and I would say, no, there is no random error that we are going to be able to predict. We're going to gray it out, make it gone, and then look and see what happens to the output after you fix that compared to before you fixed that. Something kind of interesting happens, kind of hopeful for researchers who like power. So run both. I'm sorry I can't do it for you.
How do you hide the user?
Just click on it. You click on it, and now it's it's modelable. And then when it's grayed out, it's fixed. And because that chi-square isn't significant, we get to gray that out.
Even though we're using a different outcome variable?
I can't get YIS up. No, you want to use YIS for both of them.
Okay.
Do YIS with it random and YIS with it fixed. And just look at the output difference.
yeah, how model is
Are we just basically in estimating time what is the greatest, it's almost the mode of like year most people are in high school. It would be, is it probably year 10? Between 10 and right. That makes sense.
Yeah. The idea of the reliability lambda, so our large data is reliable.
Okay, so it is very different from one group is very different from another group. And I'm going to write it out just to say it's the difference between having groups look like this and having groups look like this. Right? So it's based on n, the central limit theorem. As n goes up, we get closer and closer and closer, and n's really big. We're going to definitely not be able to detect the difference between groups, even if it's not practically significant at all, right? Hardly where that would tell us that.
We're going to change the gender. So what's this? You want to come with no gender? Yeah. No.
I know we took class today.
Oh.
I don't remember what the name was. But isn't it just like your T value?
Yeah, there's random errors. Yes.
should be okay because
All right, so we are trying to
it's
use
greater
it.
than we fail to reject it, so we do need
This, oh, this one, is equal to, so you get to the line, there's something more than, I'm sorry, this one.
some of the variances are the same.
Yeah, and so what it tells us about the city, how is that, is looking at more than that, try to something, but there are other sort of road.
That's what
Are we here? Yeah, you're doesn't matter. That's a very point.
inside the not a model.
You guys getting the big take home point? Because it's real big. What is that? See how big it is? Why do you think it's so big?
You back out.
You want school districts to more become
Oh, that's just that everything's zero. So, it's really important here is,
when you say depending on when you say that
Do it.
you want
Like, you know when you have those like deep muscle itches?
oh, yeah, price purchase is fixed.
Okay, right.
There's no tax. We don't have any, this is also, there's no tax. You just got so much power. But I mean, instead of having a school field, you get to have 480 people. Yes. We can see all the random yes. Yeah, it's, this is.
And we're just saying what you're evaluating.
So this is pretty much me. Okay. Okay. But it's just an idea that is something completely different. You lost that second level altogether.
So in that circle there, we completely, everything.
Everything is now. Exactly. And there's just a little bit.
Yeah. Random effect of being an individual.
Exactly. Which is so.
So,
Right.
yeah, I'm
That's
not
what
sure
duality.
Okay.
Okay. But what if you took your sexual awareness, which is beautiful if you do it, and you get all your it's as if everybody were all in one. Instead of having everything. So, oh, if you're looking for trouble, I really want to punch you. Is there a fun one?
Yeah, you make your intervention fail.
Or whatever you find that I'm like trying to do something, but you go, oh, you're not taking it. Those people are actually nested because people are aged and something's wrong.
But there still is no sort of.
Okay, all right. Look, there's nothing. So now everybody can just be a person and they don't have to
Go back to just regular progression.
where you run in May or June or July. People are born in particular months.
Yeah.
So it's nice to say.
Yeah, I see what you mean. In some instances.
Sometimes it's just it doesn't matter. For you, no, I'm all about you know, you want the big one. That's why that there. Just kind of look at these different. Yeah. How are we doing? Can I have one of your food? Thank you.
Yeah, I know what way before I started going to school.
I ran the test this year.
And?
So if somebody is greater than so I can
Means that you fail to reject the They are homogeneous. Yeah. So the thought is that they're the same. And you don't get to reject them. Usually we want to. In this case,
So they are.
they're the same.
They did make the assumption. But definitely isn't that.
We want, that's what I'm saying, normally we want to reject them. Like, that's our job, right, so those differences. But in this case, we don't want to reject them. We want them all. We
want the variances to be the same.
Yeah, that's nice.
So you have similar variances.
Right, so on level one.
Very the error had that second between group effects that we were able to look at. They went away when we started predicting years in school instead of predicting GPA. So when we fixed that, we had some interesting things happen. When you put them side-by-side comparison, we actually lost count. There was no such thing anymore. We took out group. So if you look at the model, there was no between group. All there was an subject variance. Disappeared. Also disappeared the chi-square, which is out. We didn't need anything to do. Now, Jennifer and I have a different opinion because I love it when that happens and you get to fix your effects, because that means you're not having to model these things that you don't think matter, because they don't matter. But sometimes the game of hierarchical linear modeling is we want these things to matter. We're doing this at all. We want between group effects. Do you want to print it? Sure, come on.
This is the one that makes sense.
Change your output variable to whatever it says. So we lost child, we lost archive because we have no second level. And the other thing that happened that was really interesting is our degrees of freedom went through the roof. Instead of 6 groups, 5 degrees of freedom when we look for the difference, now we have 485 degrees of freedom. Oh, our reliability went in. Because we don't have any between groups. But I just wanted you to look at those things. The next thing is to this homogeneity of variance. It's not hard. What were we doing?
Discussing.
Running in a map. Whoops. Other settings. We did a hypothesis test, and we just clicked that little box that said homogeneity of level 1 variance. And we said okay. And when we look at the very bottom, where is it?
I think you have to run your model. It's the same thing.
Okay. Right.
They figured out for me.
I did forget to see that little black box. Here we go.
Also, we used to change the outcome variable to GPA instead of business school.
I was thinking you just keep it the same, but you can do whatever you like. Oh no, you did it right. This one isn't hard, right? There it is. As research, we love to reject nulls because that means we have effects. But there are some nulls we don't ever want. When we do Levine's test, we don't want to reject the null. And when we run this homogeneity test, we don't want to reject the null. We want to say that the subjects are the same within their schools as far as their variance. So the variance in schools is the same. That's the null hypothesis. We test against the null. We get a p-value greater than 0.50. We reject the null, or we fail to reject it. Fail to reject the null. We say yes, the null. We don't ever get to say null's true. But we're not saying it's false. We have reason to believe that the homogeneity is equal, and that's an assumption of regression and ANOVA and everything. That's parametric. Yeah. Now this third part, I see people are having a little bit of questions about. So I was going to go over how that's played out. Oh, I should be reading the instructions, not just the After most jobs, I'll put it up.
Oh, I thought you were saying. The GOO is equal to 0.
Okay, so we ran a model predicting average GPA, and at the school level, we said we like to think that whether you're on the east side of State Street or if you're on the west side of State Street, would have something to do with how well you perform in school, right? Reasonable hypothesis. Does it look like that's actually the case? No. But we can talk about it. The expected GPA of a person nested in the group coded as 0. And I can't remember if I coded east or west to 0, but it doesn't really matter. The people in the group coded as 0 have an average score of 2.37. That's their average GPA. Okay? The group coded as 1 is going to have an average GPA, and it's so the change in 1 unit from 0 to 1 is on the y variable, on GPA, on the x variable, on the predictor, is accompanied by a change in how much on the y variable. Well, moving from the east side to the west side to the east side, your average GPA increases by 0.37. So you can add 2.36 plus 0.37, 2.73 is our expected value for a GPA for the people on the side of the street coded as 1. Okay? Pretty important to know where to find those. This is where we build our regression equations, right? We wanted to say the person's score on y would be equal to some y-intercept plus their slope times, in this case 1, their score on the side variable. So that is, those are your parameters for your regression. There's something else there too. Is there a significant difference between schools coded as 0 and schools coded as 1?
No.
Where would we find that?
Isn't it the second p-value?
Yeah, no,
But-
39.
But you're using the...
Yeah, up and down.
Yeah,
Oh,
you're using...
I'm sorry for everything I just did, huh? Yeah, the that robust model, and that robust model will get you too, because those values are so appealing. But they're not yours, almost ever. So we have to go with 0.052. Significant? No. We don't gain significantly by moving from the east side to the west side. Then after we added side to the model, even though it wasn't significant, does this leave anything in between gradients to predict? Is there anything left worth predicting on that between the good gradients?
Is it chi-square value?
Exactly. There's the chi-square isn't significant. If the chi-square isn't significant, then tau is significant. So we're not going to do anything else for ourselves by adding any variables to between the variance. I mean, we added something on non-significant, but it stopped up a little bit of variance and it brought us to nothing. So you're now through 2 pages of our thing.
Question, could you slow down? Sorry, I'm far behind.
How far are you thinking?
Yeah,
Oh, I just got one.
yeah, just started. So the GPA, so that's what she's added.
Oh, I just got it.
Maybe I can touch it wrong.
Oh. Hey, we survived.
That's great, that's the most important thing.
Yeah.
It is different.
Like that. Maybe they don't need to come up with so that's
And community on
I think it was just like you include last time we go click them up and turn it
So the y intersects the y intersects I,
Oh, you said it. Yeah, no, not center. That's fine.
Which ones for the H will go?
Yeah, so we always know the normal.
Yeah, setting the piece will also
Oh, that one is good.
but so basically when setting the goal versus that increase.
And that's what I did is zero. Oh, if you go to 0 and 1, a 0, moving 1 unit, slow. And so it's just a measure.
You're right on that.
No predictors. And then we're going to run a new model with both of the predictors. And we're going to get that cow. And the formula says the tau with no minus the tau with 2 divided by the tau with no is equal to basically effect size. The proportional variance accounted for by those two variables. So you're just going to run it twice, save those taus, or I like to keep them both up on the same screen so I can look back and forth. I think it's so neat to see what the numbers do. But then you're almost done. 10 more.
So the difference is the first one is
We already done, that was the first one we did.
Oh, I think it's T. Yeah. This will be the same, right?
Yeah.
But the ratio is going to be bigger because of our. Close. So those are like.
There's no difference. So this also is the same.
I hate how the top one HL
Well, I did. The first time I read it,
That's so many.
Yeah.
You are rich in data.
Sorry,
And average.
so we use this one.
And is that what you got?
add on the
So you're done?
No, you're. So she's saying that that equation that she gave us up there, that that's what it is now? Yeah, that's right. That is exactly what we did.
Did you do that in class today?
Hey, your computer's loud. Yeah.
Come on, I didn't pen. Somebody.
So does somebody have a calculator? Calculator? Over here.